Okay, so today we have to simplify these expressions, the radical expressions. Do you know the meaning of simplification of radical expression? So please keep on watching this video to learn that. Hello everyone, welcome back to Dona's Academy. So today I am beginning lesson 4 of pre-calculus series. Before watching this, if you haven't watched, please watch lesson 1, 2 and 3. I have copied the links below, and also you can see the iCard for lesson 3. Alright, so let's begin. So simplification of radical expressions. So before this, I think in lesson 2, I was explaining the meaning of simplifying expressions with exponents. So there was a definition for that. Similarly, we have a definition or a meaning for simplification of radical expressions. So first, let's see what it is. So I'm going to explain the meaning first. Meaning of simplification of radical expressions, okay? Alright, so originally we have a radical expression given. Then after simplifying it, we should have another expression where another expression, and in this expression the radical pieces, there should be a special a couple of conditions. The radical pieces should satisfy a couple of conditions. Now what are the conditions? In those radical expressions, first of all, the radicand, right, the inside thing should be simplified, right? It is an expression with exponents. Now you know how to simplify those, so it should be simplified first of all. After simplification of this radical, simplified, and this index n, you know the name of that index should be bigger than, n should be bigger than all the exponents. All the exponents of the factors of the radicand, okay? N should be bigger than all the exponents of the factors of the radicand, okay? Strictly bigger than. It can be equal. If it is equal to one of the exponent, then it is not simplified, okay? Alright, so these are the conditions. So let me recap those. So after simplifying a radical expression, we should have another expression where in the radical pieces, the index should be always bigger than all the exponents of the factors of the radicand, and the inside radicand should be simplified expression. So let me give some examples. How about this? So is it simplified or not? My first example is we have third root x5 y2. Now, is the radicand simplified? Yes. we see positive exponents, and we see only we see each term xy only once, right? However, what can you say about that index condition? Is it satisfied? No, not at all, because this thing is bigger than this index, right? Even though this is smaller, right? This is not satisfying that condition, and it should be for all the exponents. Okay, so this is not simplified. Not simplified. How about this expression? Fifth root of x cube y square. First, we have to check the radicand. Is it simplified? Yes. How about that index condition? It is also satisfied, right? So we know that 5 is bigger than both 3 and 2. So it is simplified. So this is simplified. All right. Okay. Now this is the meaning. However, in some cases, you may see radical expressions where the radicand is a quotient, right? A quotient. Like, for example, the second example I was talking about at the beginning, this is a radical expression where the radicand is a quotient. So if you are simplifying this kind of radical expression, there should be another condition after simplification, right? The other condition is the denominator should be rationalized, right? So let me explain what it is. If the radicand is a quotient, there is one more condition for simplification. The other condition is the denominator should be rationalized. Now, what is that? What does that mean? What's the meaning of rationalizing a denominator? So, for example, if you have something like this, fifth root of x divided by y square. Now, let's think about the condition we were talking about at the beginning, this condition. Does this expression satisfy these conditions? How about simplification of the radicand? It is okay, right? It is simplified. And how about the index condition? It is also okay, because 5 is bigger than both 2 and 1, right? 1 means this exponent here is 1, right? Okay, so we can say that it is simplified. However, since the radicand is a quotient, we have to have this condition too, right? Denominator should be rationalized. Now, denominator is not rationalized if the denominator contains this type of term where m is smaller than n. Okay, so here in this example, indeed we can split this in this way using the laws, right? So you can see that this exponent is smaller than this index, right? In that case, we say that if the bottom or the denominator contains such term, we say that the denominator is not rationalized, right? It's not rationalized. So how do we get rid of that? How do we rationalize the denominator in that case? Now, what if, now suppose we have this thing, right? Denominator, we have this type of term. Now, how do we eliminate that, or how do we rationalize? All right, so rationalizing means we have to have integer factors, right? So I mean, like, I will explain it. So now if I multiply, we have this, and if I multiply both top and bottom by this factor, nth root of x n minus m, right? I have to multiply both top and bottom so that I do not do any change to the original expression. Now what if I multiply both top and bottom by this factor? Then let's simplify. Now in the top I have this. In the bottom, if I combine using the laws, then what I have is xn times xn minus n. Okay? Alright, now I see some cancellations, right? I can cancel this thing with this negative m power. Then what is left is this thing in the top and nth root of xn in the bottom, right? Alright, so once I have this step, then I can simplify the bottom to just x. Okay? Alright, so I have rationalized. Now the bottom doesn't contain any radicals, right? Only a pure term. Right? You see only a pure term. No radical pieces. So that's the meaning of rationalizing a denominator. Okay, so whenever you see this type of pieces in the bottom where the index is bigger than the exponent of the radicand, then you can use this type of method to eliminate the radical pieces and to come up with a pure term. So that's the meaning of rationalizing denominators. You can understand this more when I go over examples. Okay. All right. Now there is another thing I have to mention. Now, when it comes to a number, if you have to simplify a number like this first example, this one, then we don't see like if you think about this condition, right? It seems like it's already satisfying these conditions. However, when it comes to a big number, simplification means you have to think about the prime factors of the radicand, right? 320 here, 320. You know how to find the prime factors, and then think about the powers of those prime factors as exponents and go with just follow these conditions with prime factors. Okay. All right. So I think we talked about a lot of things about the meaning and the special case of where the radicand is quotient, and you know how to simplify. There is another condition, denominator should be rationalized, and when it comes to a number, you have to think about the prime factors. Okay. All right. So let's directly go to some examples now. Now in these examples, I consider X, Y, Z, A, B, whatever symbols, right? So in order to simplify the cases, I mean, like when it comes to a negative radicand and when it comes to even indexes, you have to be careful with the outcome, right? We were talking about in lesson 3. So in order to simplify, for simplicity, right? For simplicity, let's assume those X, Y, Z's are positive, right? So I'm assuming for all the examples I'm considering below, I'm assume X, Y, Z, maybe T, V, A, B, C, whatever symbols are positive, right? Unless otherwise specified, you can assume the symbols given are positive. However, if you see numbers, negative numbers, then it's not that case. You have to be careful with the outcome of negatives and absolute values, blah, blah, blah. Okay. All right. First example. I'm taking the same number example. Third root of 320. I said that when it comes to numbers, you have to think about the prime factors. So let's find the prime factors first. 320. Let's divide this by 2 first. 160 and 80, 40, 20, 10, 5. So this is same as the radicand can be written as 2 to the power 6 times 5. Okay. All right. Now let's think about now how about the conditions? Now the index is still smaller, right? Index is still some smaller than the exponent 6, right? Even though this is 1, this is not smaller. Okay. Now I can use the lows. Third root of 26 times third root of 5. This piece is already satisfying those conditions, right? However, this is not. I can, now since I have 3 here, if I have 3 as an exponent, then I can simplify it using the properties, okay? So I can rewrite this as 2, 2, 3 as a power of power, right? All right, now I see 3 here and 3 here. That means this thing is same as 2 to the power 2 or 4. And here I have this piece. Is that simplified now? Yes, the only radical piece we see is this thing. And this index 3 is bigger than this index 1. So we are done. So this is the simplified version. This is my answer for this question. All right, next one. Let me take a rational one, okay? Fifth root of 5x 7 y square 8x cube. Okay. All right. Now, first of all, the inside, the radicand should be simplified. We see x in 2 places. So in order to get rid of that, let's use the lows. If you use lows, I get x4 y2 divided by 8. Now this is satisfying the index condition because 5 is bigger than both 4, 2 and 1s. However, the denominator is not rationalized. The denominator contains this term 5, 8. To rationalize the denominator, what can we do is, now I can write 8 as 2 to the power 3, right? However, I see 5 here. Now what if I multiply both top and bottom of the radicand by 2 to the power 2? 2 to the power 2. Right? Then I get 2 to the power 5 in the bottom. I have 5 x4 y2 and 2 to the power 2 is 4 actually. So I have 20 in the top. divided by 2 to the power 5. Okay, now if I split this into two pieces, fifth root 20 x4 y square divided by fifth root of 2 to the power 5, which is 2, right? Okay, so I get a pure number, no radical pieces in the bottom as before, right? Before we had fifth root of 8 in the bottom. However, now we have a pure number. All right, so that means the bottom or the denominator has been rationalized, and the inside the radicand piece is simplified, and the index is bigger than all the exponents. So we are done. So this is the final answer. Okay, all right, so we talked about two examples. My third one, fourth root of x7 y12 divided by 125x. All right, so let's simplify the radicand first. Then it's going to be x6 y12. Here let's write 125 as 5 to the power 3. All right, now the radicand is simplified. However, the index condition is not satisfied. So that means, and also the denominator is not rationalized. So first we can split our x term. Since I have 4 index here, I can write, or I can split x to the power 6 as x4 times x2, and this y, the index is 12. It is a product of 4, right? So that means we can rewrite this as a power of power. Okay, and to rationalize the denominator, we have to have one more 5 in the bottom. If you have another 5, then we are done with the rationalizing. However, don't forget you have to multiply both top and bottom by the same thing. All right, now let's split this. In the top I have this and this, y cube 4 4 and 4 5. In the bottom I have fourth power of 5 to the power 4. All right, now let's simplify. First I have an x, fourth root of x square, fourth root of y cube to the power 4. That means just y cube, and fourth root of 5. And in the bottom I have 5, a pure number. That means now let's rewrite them nicely. I have xy cube and fourth root of 5x square divided by 5. All right, so it is satisfying all the conditions. Denominator is rationalized, and the radicand piece is simplified, and the index condition is also satisfied. So this is the final answer. All right. Okay, so let me talk about a couple of negative exponent examples next. Number 4. Now I have 9x negative 4 y6. Now whenever I don't see any index here, that means I have to write square root. All right, now first of all, the radicand should be simplified. So let's do that. We should not see negative powers or negative exponents. All right, now let's write the index 2. It's not satisfying the rationalizing condition and the index condition. So let's do that. Maybe since 4 and 6 are multiples of 2, it's easier. Now we can rearrange this in this way. This is 3 square, right? 9 is 3 square. This is y cube square. And this is x square square. Now let's split this. This is easier. 2, 3, 2 and y cube 2. This is x2, 2 square root. This thing is 3. Here I have y cube and then I have x square. Right? So all the conditions are satisfied. We don't see any radical pieces, so we don't have to worry about those conditions, and the rationalizing denominator is rationalized. So this is the final answer. Okay, my last example. Something with negative numbers. 3t4 v square third root of negative 9, right? T negative 1 v4. All right, now what can we do? Let's get rid of the negative exponents first. Maybe we can combine these three because both are third root, right? First combine them at the same time. So when combining the numbers, we can multiply. So we get negative 27 because 3 times negative 9 is negative 27. And if you combine t4 with t minus 1, we get t cube, right? And v6. All right. Okay, now this is easier. Now this is same as third root of negative 27, third root of t cube, and third root of v6. v6 can be written as this. All right, now what is the third root of negative 27? Negative number and the index is odd. So it is defined as a real number. So it is what? Negative 3, right? Because negative 3 multiplied by itself 3 times giving you negative 27. So this is negative 3. And here I have t, here I have v square. And that's it. This is my final answer. All right. Okay, so we talked about the meaning of simplifying a radical expression. There are a couple of conditions we have to satisfy: the simplification of the radicand and the index condition. And when it comes to quotient case, if the radicand is a quotient, there is another condition, an additional condition we have to satisfy, that is rationalizing the denominator. We can use this trick to rationalize the denominator. And we talked about simplifying numbered radical expressions. If we have just a number inside, you have to think about the prime factors, and then we considered a couple of examples for simplifying expressions. All right, so I think you learned the meaning, and when you know the meaning of simplification, you know how to stop your calculation, right? Otherwise you don't know whether it's simplified or not. How do you know? So that's why this is important to learn, right? The meaning. All right, so you learned the meaning and you learned a lot of examples. So I think you enjoyed the video. However, before that, I have to give you a warning. What warning do I have to give? Now, in these examples, the numbers, these radicands are multiplications or divisions, quotients. However, you have to be careful when it comes to additions. If your radicand is an addition, like this. So this is a warning. So for example, if you have this thing, a square plus b square, can you write it as a plus b? Not at all, right? This is completely wrong. This is not equal to a plus b. So be careful with that. You can't apply those laws, properties if you have additions, right? So similarly, you can say this thing is not equal to square root a plus square root b. I have seen this mistake. This is a common mistake. I have seen this mistake. So many students are doing this without even caring, right? So be careful with these types of common mistakes. Okay. All right. Thank you so much for watching. So I will continue this series by uploading videos continuously. Please subscribe to my channel if you haven't done already, and like the video and share it with your friends. Okay, so have a nice day and stay tuned.